In the last hour, I was talking about the complexity of computing local min-max equilibria, local Nash equilibria, and the hardness is already held for local min-max equilibria. So let me give let me explain. I gave you some intuition about why even an extra player in a non-concave game can make even local solutions intractable. And I made this comment that sort of like we have intuition about how we would like to prove or at least query complexity lower bound, but we didn't know how to do it before, unless we first build a complexity proof and then appeal to that to properties of that to get the query lower bound. So let me discuss a little bit the types of techniques that we use, and the reason I think this is interesting, if you haven't seen this kind of arguments, is because like typically in ML, when you want to prove a query complexity lower bound, like the one I stated earlier, like this one here, that any first order method needs exponentially many steps to do something, typically, in optimization, you don't use the kinds of tools that we use here. So let me explain a little bit, what tools we use and, what is their mathematical nature. So these tools are ultimately topological, and they relate to fixed points and combinatorial arguments that are useful in proving fixed point theorems. And let me present to you a variant of the classical Sperner lemma, which is used to prove Brouwer's theorem. So this is not the original Sperner lemma. It's a variant that is convenient for us to use for our purposes. So here's the idea, and I'm showing it in 2 dimensions. You can generalize it to any dimension. So in 2 dimensions, you're going to have 2 colors, 4 colors. In d dimensions, you're going to have 2 times d colors. So in 2 dimensions, you're thinking about the grid, the square grid, and you're going to be coloring the vertices of the grid with these, 4 colors like red, blue, orange, and green. And the boundary has to look like you see in the picture. So I fixed the boundary coloring to be that. And the claim is that no matter how you color the internal vertices, there's going to be at least one square where you're going to see red and yellow together, or blue and green together, or both. Now, there are 4 colors that I'm using here, and there are 6 pairs of these 4 colors. Out of the 6 pairs of these 4 colors, 4 pairs are trivial because they come together already in the boundary. Right, so like blue, red come together here, and so on and so forth, right? So 4 out of the 6 combos of colors, pairs of colors, come together at the boundary. The claim of the lemma is that the non-trivial ones will come together no matter how you color the inside. So for example, if you were to color the inside in this way, there's a square where red and okay, this is yellow, okay. So red and yellow come together, and blue and green come together. All right. So that's the claim. So let me try to prove it. Okay, let me forget about the location of that square where cool things happen. Is that a question?
Or so you don't need both red and yellow and blue.
Yeah, or. It so happens in my picture that there is one square where both combos arise, but the claim is that at least one. There's going to be at least one square where at least where either red and yellow are going to come together, or sorry, where red and yellow come together, or blue and green, or both. Okay, pairs. Okay, so let me forget about that square where it is, and tell you how to prove that there is such a thing. To prove it, I'm going to imagine this is a factory, and the factory has square rooms. Every room has 4 pillars that are colored with these 4 colors, with different colors. And I'm going to do a walk in this factory. And I'm going to enter the factory through this door here into that room over here. Okay, so that door, no matter how you color the inside of the square, that door is certainly a red-blue door. And I'm entering into the factory having through a red-blue door with red on my left. All right, so now I enter into a room. And well, and then I find another red-blue door that I can cross with red on my left, and I do that. Okay, and I keep going. So my modus operandi is that I will enter rooms through a red-blue door, having red on my left. I will mark the door that I use to enter those rooms. And if I can find another red-blue door that I can use to exit, having red on my left, the room, I will cross that door and mark it. Okay, this is my modus operandi. So, I keep going inside this factory, crossing red-blue doors and like crossing them out. Another question is what's going to happen to my walk? Okay, let me make some observations. First observation is I will never exit the factory. The reason I will never exit the factory is that there is no red-blue door on the boundary that I can cross to exit the factory, having red on my left-hand side. There's only one red-blue door, and that's here. And that red-blue door cannot be used to exit, let alone that I will never, because the first time I cross it, I mark it, I will never use it again anyways. But so I will never exit the factory because I have to stay inside. The other observation I'm going to make is, of course, this factor is finite. There's a finite number of doors overall. So, I never cross a door that I have marked. So my walk has to stop. Okay, so I will not exit, and I will have to stop somewhere. Now let's understand where I stop. Third observation I'm going to make is the following: like no matter how you color a square with these four colors, that square can have either 4 red-blue doors, or 2 red-blue doors, or 1 red-blue door. You cannot have 3 red-blue doors, interestingly enough. And also, if it has 4 red-blue doors, it has exactly 2 doors that you can use to enter into the room with red on your left, and 2 doors that you can use to exit the room with red on your left. So these cannot be possibly rooms where I stop, because the first time I enter them, I mark the door that I used, and there is definitely an exit door. And if I ever come back to them, there will be an exit door again, because there are 4 doors, exactly 2 entrances and 2 exits. Okay. The same is true for rooms with 2 red-blue doors. If a room has 2 red-blue doors, exactly 2, one is an entrance and one is an exit. So that's also not a room where you can stop. All right. So my room cannot exit. It will have to stop. It cannot stop at a room with exactly 2 or exactly 4 red-blue doors. So it has to stop at a room with exactly 1 red-blue door. Now guess what these rooms are? These are rooms where red and yellow meet or blue and green meet. And this is what's happening here. So this is the proof of Sperner's lemma. Now you can use this. This is a variant of the more classical Sperner lemma. You can generalize to many dimensions, and you can use this to prove Brauer's-Fixman theorem. So it is intimately related to complexity theory. In fact, if you have access to the colors of this factor, if this is a big factor and you access the colors through a circuit, it is PPT complete hard to find, to identify rooms where the right combos of colors meet. All right, what does this have to do with min-max? Well, imagine, we're in many dimensions, but imagine along some dimensions you have a minimizing players' moves, along the other direction of maximizers. So let me show the picture for 2 dimensions. What does it have to do with Sperner? Well, imagine that, like I look at my loss function and I compute this gradient field. So I take the minus gradient with respect to the x player and the plus gradient with respect to the y player. and look at the direction in which this vector field is. And use the Windows colors to to color that node. Okay, so for every point over here, okay, let's discretize it. You compute the direction of the gradients and color that point using those, depending on the direction of that color. You may see a picture like this. And okay, like suppose that if you do that, the boundary coloring satisfies the Sperner properties. If it doesn't, you can argue that the problem becomes lower dimensional. So at some point you're gonna, unravel that and stop at a place where you can actually argue that this boundary coloring works. So let's say that it works for our two-dimensional picture. So if the preconditions of Sperner's lemma hold, there must be a point where red meets yellow or blue means green, okay? And the way I have arranged the colors, like if these two guys meet, both signs of the X gradient coexist in a small neighborhood, and both signs of the Y gradient coexist in a small neighborhood. If either of these combos coexist in a square, imagine these squares are very, very, very tiny. If either of these combos, if this combo exists in a small locale, or this combo exists in a small locale, then all the signs of the two gradients coexist in a small locale, and that's enough for a min-max equilibrium. And the coexistence is guaranteed by Sperner's lemma. Right? So this is how you can map min-max optimization to finding Sperner squares. Yuval.
What are the color
The windows. So the colors, depending on the direction of this gradient field, depending on where it points, you're going to call, like, if this vertex, you go to this vertex, you compute this gradient field, and if it points this way, you're going to, in any of these angles, in the positive orphan, you color it red. Okay. In this orphan, you color it blue, and so on and so forth. Okay? So now, if it so happens that you color using this protocol, and the boundary satisfies Sperner's constraints, Sperner lemma constraints, then Sperner guarantees that there is a neighborhood where all the colors meet. Not all the colors, either this pair or that pair meets. And if you get red and yellow coexisting, then at the red point you have these signs for both gradients, and the other point you have these signs for. So you have for both x and y both the plus and the minus direction coexisting. So that's enough for a local Nash. Does that make sense? So if in a small neighborhood, if in this point, for example, you point this way, and in this point you point that way, then for the X player in a small neighborhood, imagine this is like very tiny. This is tiny, like the length here is tiny. In a small locale, you have a point where you have both signs for the X player, and also both signs for the Y player, and that's enough for a local Nash. Okay. Right now, if the boundary coloring, as I was saying, does not satisfy Sperner constraints, you can map that down to a lower dimensional problem, and you can continue until eventually you can actually map it to a Sperner instance. In fact, this is what we do in a recent work with Noah Golovich, Manolis Zabetakis, and Daskalakis. So what we do is we actually, inspired by this mapping from local min-max optimization to Sperner, we take the sizes of these squares to 0, and that gives rise to a continuous time dynamic that we call SCD, okay, not GD, Sperner continuous dynamics, SCD, which is a second order method with the following property that it is guaranteed to get to a local min-max equilibrium. So prior to this work, there was no dynamic known to exhibit guaranteed convergence to local min-max equilibria. There's a paper called Follow the Ridge, which exhibits local convergence. Our method is closely related to Follow the Ridge, but it has the property that it has a guaranteed convergence to the local min-max equilibrium, albeit it's not going to be efficient because the problem is intractable, right? So we're not going to solve PPAD, but we have at least guaranteed convergence. Maybe coming back to the practical questions that were asked earlier, you can try SCD in your setting. SCD is sensitive to second order properties of your function, and like if it finds places where it's smooth, it telescopes fast inside the domain. So it's possible that in practice, if if your domain is not very rugged, that this method could be a nice method to run. Manoli.
My question is the turning, because how much smooth is the dynamic? Smooth continuous. I don't know what is the issue, but I feel that there is an issue when we do the turns, because
so the turns, so there is like the direction in which you move has to do with certain Hessians that you complete along the way, and if these Hessians are smooth,
there is a discontinuity in the turn.
There's no discontinuity. No. So it's going to be. I mean, it's it depends on properties of Hessians of your. If you have very small eigenvalues of things, that you may have sharper turns, but so it depends on what you want to assume.
For example, I see the orange box, and I see the corner. Do you see the corner in? That came in my mind like non-differentiability. Maybe it's
no. That's just a picture.
So I remember from old-fashioned Sperner that there were an odd number of triangles.
Correct. Yeah.
And I assume there's an odd number or something like that here. And so I just wonder how much topology we're going to have to learn in the future to kind of read out structural properties.
Yeah. So you're right.
Surfaces.
Yeah, you're right. So Sperner's. The Sperner triangles are going pairs. Going pairs, and there's not one left out, so there's an odd number of them.
Is that an artifact of triangles, or is it?
That's so over here they also come in pairs. So but here you have twice as many as you would have in the normal Sperner. So you lose a bit of that, but they are oriented, so you can recover it if you look at the orientations of your space. So then this actually is
So we have nothing to say about Nash, local Nash, how many local Nash there are?
No, because then I do compactness to pass to the limit and I lose all that data. Okay. So now let's look at the reverse, right? So this was intuition, like why Sperner is central in computing local Nashes. Now the question is, why are local Nashes as hard as any problem in this class? Some intuition about that. Well, you have to go in the reverse. You have to start with an instance of Sperner, like the one you see here. And you have to construct a smooth non-concave two-player zero-sum game such that if you find the local Nash equilibria there, you recover Sperner squares in your instance you started with, which would imply the PPD completeness result I want to prove. So roughly speaking, so we're not going to assign this dimension to one player and this dimension to the other player. That's not going to be what's happening. Instead, what we're going to do, roughly speaking, what I'm about to present is not going to be a smooth function, but it's good intuition. Roughly speaking, one player's job is going to be to choose squares. The other player's job is going to be to choose doors on those squares chosen by the other player. And this is where the constraints come into play. And the rewards have to do with the color and the orientation of the door that the door player chose in the square of the square player, roughly speaking. Okay. And the complication is that this is a discrete problem, but the target problem is to find equilibrium in smooth games. So how do you turn this idea into an instance of a smooth two-player zero-sum game, and that's where a lot of the work goes in this paper. So yeah, we have to do a lot of work to, take kind of like a discrete construction, map it to a smooth objective function in high dimensions. So doing smooth interpolation in high dimensions is not as easy as you may think.
Smooth, like Hessian Lipschitz, or is that?
Just gradient Lipschitz. Yeah. To do it in a computational efficient way, right? Because in the high dimensions, you have a d-dimensional cubelet, and it's exponentially many corners. So the obvious construction is not going to work for you. So you have to divide into simplices, but these simplices have boundaries. And as you traverse boundaries, you may lose the smoothness if you do the standard interpolation. So a lot of work goes there, how to interpolate in high dimensions efficiently without violating smoothness. All right, so that's roughly speaking what I had on the complexity front. But what I want to draw from that, and like, don't throw tomatoes or eggs at me, but I want to draw a philosophical corollary out of this. All right, my claim is that because of these complexity results that arise in computing local Nash equilibria, we cannot extend the deep learning paradigm simply to the multi-agent setting. Because we cannot just say, look, I'm going to endow all my agents with the ability to run gradient descent, give them complex models, give them utility functions, and let them gradient descent the hell out of it. The complexity result says that, in principle, it could take exponential time to converge. So, do we want our TensorFlow to converge in exponential time? No. Okay, so we have to be a bit smarter about the situation at hand. We have to do a lot more work. We cannot just blindly come up with any model we want, gradient descent the hell out of it. Okay, that's my point. And I think we have to do a lot more work in modeling the setting, choosing the right learning model, like the architecture of our agents, deciding what are meaningful solution concepts. Maybe it's local Nash, maybe something else. You guys will define it during the semester, this program. And designing the optimization algorithm will get there. And I think only then we will get to more successes like, AlphaGo and Libratus. Because, if you look inside them, I mean, this uses no deep learning, like Libratus uses no deep learning. And AlphaGo uses deep learning, but it uses also Monte Carlo tree search and other game theoretic ideas for how you optimize strategies in min-max around term-based problems. So my claim, philosophical corollary, is that you have to work a bit harder. You cannot just be agnostic about everything and hope to succeed.
And I just agree with you completely. It's not debatable. Except that I don't like all of the focus on worst case and adversary.
For sure.
And that's
sure.
the heritage of computer science, and it's really, we got to move beyond it. And I know some people in the room are already doing this, but
yeah, for sure.
Cooperative concepts are really necessary for us to bring real impact in the real world.
For sure.
It's not that kind. That's not real life.
For sure.
Real life is that we trust people around us. We build trust. We build coalitions and all that. So actually, I think most of the cool new solution concepts and algorithms. Sure. And we're going to be in a different setting. They're not going to be explaining deep learning.
I'm in full agreement. I mean, this modeling the setting is exactly what we should focus on. Like, we cannot just hope to solve everything in the world. We have to think about what we're trying to solve, build the right frameworks to do so. I fully agree. Yeah.
Can I ask a technical question? You said that if you have the gradient, it's exponential, but that is not the computational.
It's a query complexity.
It's a query complexity.
Yeah, so
it does
what I
not
showed,
come from the equivalence, right?
It does, but yeah, so you have to work harder for that. As it turns out, this reduction, this computational hardness reduction, has an extra property. It's a black box reduction. So you can use kind of like, you can take the circuit of Sperner and with query access to it, construct the arithmetic circuit that computes the objective function in the game, And because query complexity lower bounds exist for Sperner, you can inherit them for min-max optimization. So that's a very insightful question. Yes.
Very quickly, it just came in my mind. So it would be interesting to check if I have access also to Hessian, or to more derivatives, if the problem can become easy.
So the method that I mentioned with Noah Golowitz and Manolis and Stratis, this one uses higher order information. And as I was saying earlier, kind of like if you're sufficiently smooth, it also allows you to telescope in the space, which also relates to the point that Mike said that things are not worst case. Maybe there's more smoothness, and my method can.
So the problem is not intractable in that sense.
Excuse me?
The problem in that case is not intractable, given that I don't have guarantees that it is intractable.
You do, because PPD hard, right? I mean, like the PPD hardness result already holds even if you have white box access to the utility. Right. So the hardness, the computational hardness is with the white box access. Yeah. The query is with the black box. Yeah. All right, so let's just start jumping off point for my next part. So let me get into that. Like, we have to do a little more work. We have to understand the settings we're interested in solving. So, what should we do there? Okay. And I wanted to discuss a little bit extensive form games, stochastic games, and low complexity games along these lines. Let me start with an executive summary of what I planning to discuss, and I'm going to cover as much as I can in the remaining 35 minutes or so. Okay, so what's up with okay, so let's continuing the same token from previous hour. Okay, what will become of local Nash? Okay. Okay, it's intractable, but as I was saying, you can exploit this connection to Sperner and the types of algorithms that solve Sperner to construct these second-order methods. And these second-order methods use the Hessian, and if the Hessian is smooth, maybe you can expect that in reasonable scenarios, this SCD method may work well. Another thing that I find interesting is how to convert this second-order methods to first-order by kind of like with first-order access to your function, construct an approximation to your Hessian. All right, so turn them into
methods.
Excuse me?
Hessian vector methods, you mean?
Yeah, do stuff like that to turn them into first order, hence more efficient. And coming back to Mike's point, identify beyond worst case complexity type of a structure under which the problem is not intractable at this level of general value. Another thing that I find actually cool is the following: that a lot of our trouble with local Nash, even in two-player zero-sum games, is that the problem is min-max. So it's a fixed point problem. It becomes a fixed point problem if you have non-concavities. You lose the connection to convex optimization that you have if it's convex concave. But there are other solution concepts in economics that are not fixed point like correlated equilibrium. One thing that I find very interesting is, what is a local notion of correlation? How do you define a solution concept where your agent's actions are correlated, but in a local sense? You don't want to, of course, you don't want to have a global correlation over a high-dimensional space, but what are interesting notions of correlation that are stable at a local scale? I find that an interesting thing to think about. This is on the local side. What about global side? Okay, so like game theory is like convexifying things. So is there a way to convexify my way out of the issue? As I said, like if you don't if people choose continuous actions, the problem is the equilibrium may not exist. But maybe I can I can find the existence if I go to randomizations over this high-dimensional space. Okay, this convexify the problem. So what I want to talk about is some recent work with Noah Golowicz, where we show that the minimax theorem holds and the coarse correlated equilibrium exists if you consider randomizations over these high dimensional spaces, as long as you avoid certain bad structures that prevent equilibrium existence. Don't read this. I will get to it in 2 slides. Don't read those conditions. And we also get no regret learning dynamics that have fast rates getting to those solutions. That's another thing that I want to touch upon. And finally, it's very interesting to consider special game classes that sidestep the intractability barriers. And one important one are stochastic games. Stochastic games go back to Shapley's seminal paper in the 50s and have received a lot of work in game theory and also recently as a model of multi-agent reinforcement learning. So in these games, an important concept that I'm going to discuss are stationary Markov equilibria and stationary Markov strategies. Interestingly, the utilities of agents with respect to these stationary Markov strategies are non-concave. Nevertheless, equilibrium exists, right? So it's a non-concave game with respect to the stationary Markov strategies. Nevertheless, global equilibria exists with respect to the stationary Markov strategies. So there's a lot of structure in this setting, despite the fact that it's non-concave. And I think it's an interesting place where progress should be made. I'm going to talk about that in a little bit. Okay, so this is the executive summary, but let me dive into a few of these ideas. Okay, so don't worry about the rest of the details on this slide. Let me first talk about infinitely large games and global equilibria in these infinitely large games. Right? Is it possible to compute or learn equilibria in this when the game has infinitely many actions and you consider randomizations over these infinitely many actions? How do you approach this problem? Given the fact that typical rates for no regret learning depend logarithmically in the number of actions, right? So now I'm thinking about infinitely many actions. So I cannot just use these algorithms for that purpose. Right, so can we get learning in games with infinitely many actions if the game has low complexity? And we have to understand what is the notion of low complexity for an infinitely large game so that equilibrium existence holds and equilibria are approachable by learning methods. Note that in the statistical setting, when we learn from IID data, it is possible to avoid paying log number of hypotheses and pay something that depends on the VC dimension of the function class you want to prove uniform convergence for. So on the statistical side of things, we have experience where we don't need to pay in our sample complexity bounds logarithmically in the number of hypotheses to get uniform convergence. So can we replicate that picture in the game setting? There are issues, okay? And the issue comes in the form of this guess the larger number game. It's a 2-player zero-sum game where one agent proposes a number, the other agent simultaneously proposes another, and whoever proposes the bigger number wins. This is the utility of the purple player in this game. Let's say that we tie breaks in favor of that purple player. If players play in the upper triangle, the purple player wins a point, otherwise they lose a point. The problem is that this game has no Nash equilibrium, even an approximate one. I mean, I hope this is obvious, but if it's not, here's a little proof. So suppose a strategy P, a distribution over natural numbers for the row player and a distribution over natural numbers for the column is a quarter approximate Nash equilibrium. And suppose that without loss of generality, the game is under this pair of strategies is in favor of the purple player. Otherwise, I would do the symmetric argument for the other player. So let's say that in this approximate Nash equilibrium, the purple player more often wins than loses. So the value the utility receives is at least 0. If that's the case, okay, so of course you can always find a number x that is bigger than a big chunk of the support of the purple player. You can choose a number way down so that let's say 4/5 of the support of the purple player is below that number. If you were to switch there, you would definitely you need at least this many fraction of the time. Currently, you win lower than 0. Now you will win that, so you are improving by more than a quarter. So yeah, so this game does not have Nash equilibrium. So what am I going to do? Right? So I'm thinking about infinite games, and even when the game has a countable number of strategies and it's 0 sum and 2 player, I lose equilibrium. So surprising fact, this guess the larger number game is the only obstacle for equilibrium existence in 2-player 0-sum games. Right? So any 2-player 0-sum games with potentially uncountably infinite actions for the many actions for the 2 players, if it does not contain this guess the larger number game, then it will have a min-max equilibrium. And actually the min-max theorem will hold. So a result by Haneke, Livni, and Moran from last year says exactly that if you have an infinite game that does not have, contains a subgame that looks like the guess the larger number game, then it has an epsilon approximate Nash equilibrium, a min-max equilibrium for any epsilon you want. Yeah. Now, which games have no such? Okay, not having this, I guess, the larger number game inside you, what does it mean for you, right? What are the sufficient conditions? Are there any reasonable, conditions under which you don't have this game inside you? Here's a sufficient condition. So if your Littlestone dimension is bounded, and I will postpone a little bit to the next slide what this means, then you don't have the guess the larger number. And also this condition, having a bounded Littlestone dimension, in a sense is almost necessary. And you can look at more details in the paper with Noah Golovich, and also Nika tomorrow is going to talk about that a lot. Yes.
Just very quickly.
Yeah.
The diagonal that it is not 0,
yes.
Does it matter a lot or not?
That is not 0. Oh, I just wanted to have a binary game.
Okay.
Yeah, for this slide, I'll give you, here's a theorem for general games.
Okay.
With Noah. This is a real value generalization. These are Boolean games, minus, plus, minus 1 are the pairs, and 0 sum. This is 0 sum, but real value. So what we show is that this can be generalized as long as you don't contain a scaling of in some precise sense. You don't have a scaling, a scaled version. You don't contain a scaled version of this game. All right, so these are the interesting results that I wanted to talk about. Let me explain a little bit, at least for the Boolean case, what this means. So this is a little bit, has to go through sequential Rademacher complexity. So let's postpone that to the paper. But let me describe a little bit what it means for a game to have finite Littlestone dimension. What is a Littlestone dimension of a game? Okay, so here's our setting. We have a Boolean valid game, plus minus 1, with a bunch of players. I'm going to define the thing for multiplayer games as opposed to 2-player 0 sum. So you have an n-player game with utilities are plus minus 1s, so Boolean utilities. And for every player, you consider a hypothesis class that it's a Boolean, because this takes values plus or minus 1. It's a Boolean function here. And this function is indexed by the action of the player. So there's one function for every action of the player. So they're potentially uncountably infinite actions of the player. So they're potentially uncountably infinite utilities in here. But it's xi that you play defines a Boolean function on the strategies of the other guys. That's a hypothesis class you can define. And the Littlestone dimension of the game is going to be the maximum of the Littlestone dimensions of these function classes that I created this way. So I create a function class per player. I look at the Littlestone dimension of each of them. The maximum of them is the Littlestone dimension of the game. Now, how do you define, I mean, in case you're not familiar with this concept, it's a concept of learnability in online learning. What is the Littlestone dimension of a function class? The way you define it is you consider trees, decision trees, like the one you look here, where you query a variable, and depending on its value, you go left or right. And going left, you query another variable, you go left and right, depending on the function output. And so what you want is that okay, so we say that such a tree is shattered by a function class if for every leaf of that tree there is a utility function, there is a hypothesis that satisfy for example, like for the green path to be implementable, you need a utility function that if you query it on this point, it says -1. If you query it on this point, it says +1. If you query it on this point, it says +1. So this tree is going to be shattered by this function class if I can get to any leaf if I choose the right hypothesis in my function class. So now the deeper the deeper I can the Littlestone dimension is how deep I can make that tree so that it's still shattered by my hypothesis class.
10 points.
Correct. Yeah.
Okay, so you can actually have
Yeah. Yeah. You wouldn't gain much from that, though. I mean, in fact, you shouldn't do that because it's certainly not going to be a complete binary tree if you do that. So you shouldn't do that. So what I want is the biggest complete binary tree, the deepest complete binary tree, such that every leaf I can get to if I pick the right hypothesis in my class and go down by querying this hypothesis. Okay, that's a definition. Okay, so it takes a while to parse, but it is important for online learning. Here's a result that we can establish that not only min-max equilibrium holds if a game has finite Littlestone dimension, but also we can replicate the types of rate that Sirganis et al. Get for finite games in these infinitely large games. So there are algorithms, there are no-regret learning algorithms that converge to equilibrium with a rate, with a regret that's does not go like root t, but that grows like t to the 1/4, and a Littlestone dimension of the function class at the front. So it does not explicitly depend on the number of actions that you have available. You have infinitely many, uncountably many actions. And what the convergence here means, if you're in a zero-sum game, you converge to min-max equilibrium. If you're in a multiplayer game, you converge to a coarse correlated equilibrium of the game. So effectively, what the results say is that if you avoid this guess the larger number game inside you, if you do not contain that guess the larger number game, then equilibria exist, like min-max or coarse correlated equilibria exist, and you can arrive at those equilibria via no-regret learning at the fast rates that we know from Sirganis et al. For finite games. We haven't improved those to the most recent results that I talked about earlier, where this is polylog T yet. Okay, so we have not used this higher order smoothness technology to bring this down to polylog t, but this is the first step. Yes.
So to understand, what is an algorithm here? So you keep a distribution over actions. And,
Yes.
and if yes, how you update your distribution? You say I'm using no regret learning, right? So how you update in one step? How you update your distribution?
It is complex. It is quite complex.
Okay.
Yeah, not in a way that I can
It's not,
describe.
yeah.
It's not a gradient descent or a poly.
No, it's of course
It
not.
is complex.
I mean, you need to update the distribution.
Yeah.
Yeah.
And I'm not
Support
claiming it's an
it.
efficient algorithm. Like,
Yeah, yeah,
I'm not claiming every step of this algorithm is efficient. You have to
Oh.
operate on the whole function class.
Sure.
I'm just pinning down the rates here.
The lack of general summing the two players is something because I'm just
I mean, if you're a two-player general sum, you fall under this category. You go to cross correlated. Gauss equilibrium is BPD complete, so you good luck with that. So,
right.
okay.
Right.
So that's the first thing I wanted to talk about. Second chapter, stochastic games, and also as a model of multi-agent reinforcement learning.
Costas, on the previous one,
Oh.
do you have anything on Oracle-based type of assumptions here? Like, if you have some
Yeah, I mean, if you look at our algorithm, it makes some various kinds of Oracle. It wants to run every step. You need a certain subroutines operating on your function class. So if you have those, you can get efficient algorithms. That being said, that's a great question to investigate further. So we haven't, thought much along these lines for specific, say, function classes and so on and so forth. So we have a generic algorithm that operates for any Littlestone game. But yeah, that's an interesting thing to consider. Yeah, following up also on our work and your work with Nika and so on and so forth. Okay, so stochastic games. So what are stochastic games? So stochastic games are multi-player generalizations of Markov decision processes. So in a Markov decision process, you have a system that is reactive to your actions, like in this picture. So roughly speaking, the system changes states, and the state transitions are stochastic, and they depend on the current state and your action at that state. So where you go next depends on your current state and what you choose to do at that state. And also you receive rewards based on its transition. If you go from state st to st+1, after you've taken action at, you get some reward. And you can think of various ways to behave in such an environment, maybe history dependent or history independent. One of the important types of strategies are what are called stationary Markov policies. Stationary Markov policies are policies that specify a distribution of actions at every state and do not have this changing over time, hence stationary. And also this depending on the history of what has happened so far. They are Markov because they don't depend on the history of what has happened so far, but just where you are right now. And they also don't change with time, so they're stationary. Okay, this is what it means. The agent's goal is to optimize the reward. What is the reward? The reward is the infinite sum of the rewards that they receive in expected rewards they receive in a trajectory using their policy. And so if this expectation is, you start from some distribution sample from some initialization distribution, and on every step t, you choose an action according to your policy. You make a transition according to the transition distribution. So that produces an infinite trajectory. You sum the rewards you accumulate on this trajectory. So this is your reward from choosing in this case, stationary Markov policy. The analogous thing generalizes if you have many agents. So now the state transitions depend on the actions of everybody. The rewards that people receive, each agent receives a reward that depends not just on their own actions and the states, but also the actions of the other people. Again, an interesting object to think about are stationary Markov strategy policies specifying for each player what action they choose at every state, potential distribution of actions. And again, every agent is interested in optimizing their own cumulative infinite reward, which is given their own policy and the policy of the other people, I have an infinite expectation over the starting state, the actions that all agents chose along the way, and the state transitions, which depend on everybody's actions. And I'm accumulating the rewards that I receive in this infinite trajectory. Okay. Now, what I wanted to point out is that this function of your stationary policy is not convex or concave in your own policy, right? It's very non-convex in general, right? Because you take that policy, you use it in this expectation, you plug it into the reward function. In general, it's not convex. Even if you have a tabular, like an explicit representation of this environment, even if you have like a finite number of actions, and you have an explicit representation of this and that, your rewards are not concave in your own policy, just because you have to compute with respect to the stationary, with respect to the distribution of trajectories that can arise from everybody using their policy. So it's an interesting non-concave game. And it's super interesting because despite the fact that it's a non-concave game, Nash equilibria exist in Markov stationary strategies under very general conditions. Basically, the condition that you need is that with probability 1, the game will stop by arriving at some sync state where nothing happens. As long as that you have that, like at every round, you chip off a little bit probability going to that sync state. As long as your game terminates with probability 1, and it's not like an infinite game, an infinite trajectory, stationary Markov equilibria exist. So that's pretty surprising given the non-concavity of the utility functions in your own strategies. Right? Which is an invitation for algorithmists. Right? So you have, what do we have here? We have a non-concave game that has global equilibria in these stationary Markov strategies, despite the fact that the utilities are non-concave. So that's an invitation for us optimizers to start optimizing, trying to learn or compute equilibria in these games.
So here, your opponents they have to use stationary Markov
deviations,
or they can use any deviation.
Stationary Markov. Yeah. We play the game over stationary Markov strategies. So what do we know about algorithms? Well, on the MDP setting, there is tons of work, both for the problem of computing optimal policies and the problem of learning optimal policies in an environment that you do not fully understand a priori. I'm not going to talk about that a lot because Dylan Foster later this week is going to actually dive into exactly. Dylan has done a lot of exciting work recently on this problem, and he will do a whole tutorial on MDPs and RL. I'm also not going to dive too much on the right-hand side because Jean is giving another tutorial on multi-agent RL. But I just want to make a few remarks. First of all, the problem that I'm targeting here is at least as hard as Nash equilibria in general sum games, which are PPD complete. So it's not like some magic box like will solve Nash equilibria for me here. Like even if you have a single state, you have the enough expressivity to express any normal form game. So the problem is intractable in general. So you have to focus on special cases or special targets if you want it to be tractable. So what are these targets? Well, first target with a lot of work recently are two-player zero-sum games. So stochastic, two-player zero-sum games. There are a lot of methods recently for learning and computing equilibria in this special case, which generalizes, the von Neumann setting, and it's a case of a non-concave zero-sum game, but where you can tractably compute the Markov stationary min-max equilibrium. The other target that has received some attention, especially in very recent years, is correlated equilibrium in the multiplayer version of this game. So the multiplayer version of this game generalizes normal form games. In normal form games, there's no issue of tractability for correlated equilibria. So the question is, can you compute correlated equilibria in the stochastic version of multiplayer games? I'll talk about that a little bit in a second. And I want to carve out, and again, C-Gene is going to cover all of that. So I just want to carve out some directions from my perspective. And, and then, like C-Gene will have the floor to analyze that further. So one interesting question is decoupled methods. Lots of equilibrium computation and learning methods for stochastic two-player zero-sum games or correlated equilibria in multiplayer cases are centralized. So you have a central planner who's optimizing the policies for all the players at the same time. An interesting question is, can you get independent equilibrium learning? Can you have the types of algorithms that we know for normal form games where each player is running their own no-regret learning algorithm, for example, and the joint behavior gets to correlated equilibrium or min-max equilibrium? We don't have much of that, actually. There is some work on independent equilibrium learning. Let me illustrate one of these works that I was involved with. And also take the opportunity to talk a little bit about this very nice special case of two-player zero-sum stochastic games. One cool thing about them is that the minimax theorem holds for stochastic stationary Markov policies, despite the non-concavity that I was talking about before. So there's a lot of structure in this setting, right? So there's enough structure to have a minimax theorem. So can you exploit this structure to get gradient style or learning algorithms to converge to minimax equilibrium? There must be, right? There's a lot of structure. So does policy gradient, for example, or Q-learning or some other algorithm like that converge to minimax? And what types of structures would enable you to do so? In a paper with Noah Golowitz and Dylan Foster last year, we show that the games, the type of structures that you can exploit to argue that gradient methods work is a type of a gradient domination condition that allows you to argue that if you find stationary points, these are actually, your duality gap is small. This is roughly what's taking place. So you can exploit this structure that is there to argue that if the two agents of your game run independently policy gradient methods, then if you set the learning rates appropriately, you can get convergence to minimax. Exploiting, it's not a convex problem, but you have a lot of extra structure, and it arises in the form of a gradient domination condition. For our work, there is other work that exploits that, that does not analyze gradient policy gradients, but analyzes other learning methods. And this is a little bit of a recent theme on that front. That's for two-player zero-sum games, stochastic games. How about correlated equilibria in multiplayer stochastic games? So here we know very little, and I hope that this semester will contribute to that, to making progress there. We know very little for computing correlated equilibria in these games. And one thing I want to point out is that the Papadimitri-Ralph Garden framework for computing correlated equilibria that I mentioned earlier for games of polynomial type does not apply here because stochastic games are not of polynomial type. Deterministic strategies are what you would do in every state of the game, and there are exponentially many of those. So you do not have polynomial type. So you get, some general purpose algorithm to compute correlated equilibria for you. So the question is, what is the complexity of the problem? So some recent work on this in this space, and I expect Shi-Jin to talk about that, it has been able to solve the more easy cases of the problem where you have a finite horizon and you can do effectively backwards induction to compute correlated equilibrium. But I don't know what's happening in general, but you don't have like a finite horizon so that backwards induction works. It might be intractable, or there could be tractable variants of correlated equilibrium. That's a very, I feel like multi-agent RL is one of the interesting frontiers on the multi-agent learning space. And you know, since Nash equilibria are intractable, it's very reasonable to target correlated equilibria, but we know very little about those. So I think that's a very interesting problem to consider. Yeah.
The finite horizon doesn't have connections with correlated and sequential games, like the Bernard von Stengel had some work. Okay.
Yeah, I'll talk about that. Yeah, just next. Yeah. The other thing that another important frontier is to add incompleteness of information in this onto this problem. So, like in the stochastic game model that I mentioned, the state is fully observable by everybody, and everybody chooses their actions after observing the state. In many scenarios, of course, you don't know fully the state. Just, you know, maybe nature has dealt cards to your opponents, and you don't know what cards they have been dealt. Nature has given you certain DNA, and you don't know that unless you do 23andMe or whatever. So, you know, so there is incompleteness of information. Importantly, completeness of information arises in, you know, in Libratus and other, you know, like recent developments. And I think an interesting frontier on the multi-agent learning multi-agent RL setting is to add incompleteness of information to that model as well, and extend then, you know, a very cool line of work that we have for extensive form games, which are, you know, which are games where, you know, like the states are structured in a tree fashion, like what you see in turn-based games. So over there we have. Despite the fact that these are also of non-polynomial type, these extensive form games are not of polynomial type, we have linear programming approaches that compute minimax equilibria in the two-player zero-sum case. And we have ellipsoid against hope methods that compute a type of correlated equilibrium called extensive form correlated equilibrium. We also have an important line of work on no-regret learning that computes either this or that. And what I want to propose is generalizing those results from the extensive, incomplete, extensive form game setting to the incomplete, or, you know, some special cases of the incomplete stochastic game, information stochastic game setting. So let me wrap up by saying that, you know, min-max optimization and equilibrium computation are classical questions with intimate connections to many disciplines and the foundations of optimization and mathematics. You know, classical. They also have classical applications in machine learning and very recent applications in machine learning. Those recent applications pose big challenges because of the high dimensionality and the non-concavity of the utility functions of the agents. And you know, in my tutorial, what I tried to do is to chart the landscape of what is possible and what is challenging, you know, when you consider the types of models and questions that arise in this space. Thank you very much.
Thank you very much. Given that we went a bit 5 minutes overboard, I think we should take discussions offline.
Sure.
Many questions. Thank you very much.
Yeah. Thank you.